Hello and welcome to Toddcast number 15. This starts acid-base review, which pretty much is going to be a GChem lecture hidden as a OChem review lecture. But it's pretty foundation to what we're ultimately going to do in OChem. And I think I say that at the start of every Toddcast. So for about the first 20 or so, it really is review of other material with a little bit of OChem stuff stuck in here and there. But once we're into OChem, it'll be full speed OChem. But that will not be this one. So I want to start with an acid and base. There are multiple definitions. You learned the Arrhenius definition, which dealt with water. You learned the Bronsted-Lowry, which dealt with a protic solvent, because they talked about a proton transfer. And you learned about the Lewis definition, which dealt with lone pair donor, lone pair acceptor, and that can be done in any solvent and actually can be done in the gas phase where there is no solvent. But for most of us, we think of acid as something that generates H plus. And I just want to say I'm kind of a little bit nutty about color coordination. So acid is going to be in red because litmus paper turns red with acid. And I think just knowing that sort of thing in the back of your mind, that red is acidic, blue is basic. And a good way to remember that is the words acid in red end in D, and the words blue and base begin with B. So knowing the way litmus works helps a little bit. We definitely use litmus and litmus paper in lab to determine the nature of a solution when we do recrystallizations or extractions, different procedures. So acid red, base, source of OH minus is blue. Now these aren't the only definitions. I'm not going to say there's only H plus and OH minus, but that's the one we typically think of. So an acid, it yields hydronium, H3O plus, and water. That's the Arrhenius definition. As a result, the solution becomes richer in hydronium than hydroxide. It's defined as having a pH less than 7, which corresponds to a pOH greater than 7. We will not be touching pOH in this class, but good for the review. And then as mentioned, it turns litmus red. Base yields hydroxide when added to water. So again, that's the Arrhenius definition, generates hydroxide in water. That results in a solution that's rich in hydroxide, causing the pH to be greater than 7, the pOH less than 7, and as mentioned, turns litmus blue. Okay, just a little side note of why we care about this sort of thing. So if in your future you were to run into a question like this, where they say some compound X is treated with CrO3 and H2SO4, and what I'm hopeful from your GChem exposure, you will recall H2SO4 is a strong acid, so it's going to make highly reactive conditions. And then CrO3, you remember hopefully from redox chemistry, where it's an oxidizing agent, it's rich in oxygen, so it oxidizes. So compound X is being oxidized into compound Y. So the oxidized product is Y. And they say it turns litmus paper red. And again, this is a little bit much at this point, but I still want to go over this question logic of the information you'll gather and how it can answer this question. In OChem, the only common acidic compounds you'll deal with will be thiols, SH. It'll be carboxylic acids, CO2H, and it'll be phenol, aromatic ring, six-membered aromatic ring called benzene with an OH on it. So those are the two there. I left out thiol because thiols do not oxidize very easily with CrO3. They can, and under whatever conditions they may do it, but that's not what the reagent you would use to do that with. So CrO3 is pretty much exclusively for oxygen-based compounds. Well, this fact doesn't mean anything yet, but hopefully by the end of the semester, that'll become a key component of your knowledge base. That when you use 1700, that refers to a C double bond O. Litmus, turning litmus red means it's an acidic compound, so we're down to carboxylic acid and phenol. 1708 means it's got to be that compound. And just as a point of interest, it ends up that to oxidize that compound up to this, it has to have carbon 1 with an OH. So the compound, it probably oxidized. And I say probably because there are actually a couple combinations that could work, but the most probable would be CH2OH, known as a primary alcohol. It can also work if we're an aldehyde. Okay, so I'm going to get rid of what I wrote, and we're going to move on to the review portion of it. So that was just a little taste of the OChem reasoning why you need to know litmus is red or blue, depending on acid or base. So Arrhenius definition, again, water's the solvent. Proton donor and proton acceptor. That's the Bronsted-Lowry definition. Good way to remember it, bro low, pro do. It may sound like a fool, but it will help. So bro low, pro do. A Bronsted-Lowry acid is a bro low, Bronsted-Lowry, pro do, proton donor. So an acid, bro low, pro do. And then a base will be the opposite. Lewis again, lone pair donor or lone pair acceptor. Key thing, I have to have a pair. So I'm missing a word there. And I want to emphasize a really good way to remember this. If I want to have a Lewis base, oh shoot, I misspelled it, because to be a Lewis base, you need 2 electrons. So it's an electron pair acceptor for Lewis acid, an electron pair donor for Lewis base. So in order to be a Lewis base, you have to have an electron pair, 2 E's. There's 2 E's in Lewis base. There are 2 E's in a Lewis base. So good mnemonic. Okay, let me get rid of my terrible placement. These are considered Lewis acids. Notice the complete absence of any H plus on it, but they still can accept electron density. So boron only makes 3 bonds because it is 2s1 or 2s2, 2p1. So it has what's known as an empty p orbital. And so a Lewis base, such as ammonia, can come and attack and form a new bond. So a Lewis base is also known as a nucleophile. It will come and it will attack a Lewis acid, which is sometimes referred to as an electrophile. So let's go ahead and define those words a little bit better. Nucleus loving, nucleophile, electron loving, electrophile. So it's based on what it loves. So if you're positive, you would love to get an electron. So electron pair acceptor. If you're nucleus loving, that's positive, you must have electrons to share with that nucleus. So you must be negative to share with the positive. But Lewis bases are also known as nucleophiles. Lewis acids are also known as electrophiles. Okay, those are terminology review. We also have to remember that pH equals negative log H0 plus, which can also be rewritten with the negative to each side and take 10 to the power. H0 plus equals 10 to the minus pH. And then you can also have pH plus pOH equals 14. Caveat on that one, only true at 25 degrees Celsius. So for our class, I'm going to use that as a given. But if you get into biochem or physiology, where body temperature is 36 to 37 degrees Celsius, that doesn't quite hold true anymore. It ends up being 13.9-ish, like 13.88, I believe to be exact. Just a little fun fact that's only true at 25 degrees Celsius. Okay. So applications. Here's like a situation where an OChem molecule, this is aspirin. Aspirin is acetyl salicylic acid. This is an ACE group. We mentioned ACE, CH3 carbonyl in previous. So acyl group. When you take aspirin orally, it goes in the stomach and it gets hydrolyzed. So the word hydrolyzed, emphasize water. Lyzed means broken by water. So you end up adding an H of water here and an OH there. So you end up getting this compound right here coming off. That's vinegar, acetic acid. And that's irrelevant. That doesn't do much for us. But this compound is one that's ultimately going to be the prostaglandin suppressor, the painkiller, if you will. We can take aspirin for other reasons, but most often it is a prostaglandin suppressor. And specifically, we're usually aiming for the pain receptor, or not the receptor, but inhibiting the prostaglandin that binds the pain receptor. Okay, so we have this compound, and what is interesting, going to clear everything. What is interesting, depending on how much interest you have in biology, If you take too much aspirin, it starts to eat away the stomach lining. So perhaps this is something you've heard, but it can cause ulcers in the stomach lining. And the way it works is as follows. The stomach is a highly acidic environment. So the gastric fluids in the stomach are around 2, maybe from 1.5 to like 3, depending on what side of digestion you're on. And then so your pH inside the core of the cell is around 7.4. So what can happen, because everything is sp2, 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 that means this is sp2 because it can resonate in, this is sp2 because it's in a double bond, this is sp2 because it resonates in. So every single atom is planar. So it can literally slice, it can slice its way into the cell membrane by lining up just right, like a stingray swimming through seaweed. This can slide through the phospholipid bilayer and actually traverse through the cell membrane. It's amazing. One of the few molecules that can do it because it's completely planar, it can go in. If and only if it is neutral. So in the stomach, at a very low pH, we have to decide, will this be neutral? So this is where our good friend, the Henderson-Hasselbalch equation is going to pay dividends. That if you recall, pH equals pKa plus log of AHA. A being the conjugate base, Ha being the conjugate acid. And so by knowing pH and pKa's relationship, you can know something about the HA, the protonated form, and A minus, the deprotonated form's relative concentrations. So I'm just going to think about it this way. When the pH is less than pKa, we'll do it conceptually first, and then Henderson-Hasselbalch second. When pH is less than pKa, it's considered to be an acidic environment. And so 2 is less than 5, the pKa of this carboxylic acid, and 2 is less than the pKa of this phenol. So I want to go back to that example I threw earlier. Mentioned that carboxylic acids and phenols are both acidic. They're the two acidic compounds you have in organic chemistry. This happens to have both those functional groups on the same one. So salicylic acid, carboxylic acid, and a phenol on the same compound. Okay, so just random fact, that's part of the reason why I want to do that molecule earlier, but carboxylic acids and phenols, OH on a benzene ring, are acidic. pKa's of 5 and 10, 2 is less than both those, so pH is less. If the pH is less, then it's an acidic environment. When it's acidic, it will stay protonated. So this is going to stay as an OH, this is going to stay as an OH. And so our conclusion is that it's going to be a neutral molecule. So the pH is less than pKa, it's an acidic solution. Under acidic solutions, things get protonated, so protonated exceeds deprotonated. Hence, it is a neutral molecule. It can slide into the cell membrane and actually traverse all the way across the cell membrane and enter into the parietal cells or the surface cells of the stomach lining. When it does this, the environment now changes. The cellular pH is mentioned, intracellular within the core of the cell, is 7.4. 7.4 is higher than 5. It's lower than 10, so I'm not going to worry about 10, but because it's higher than 5, this side right here, we have to see what will happen to it. Because pH 7.4 will be deprotonated, it's going to become negative. So the deprotonated form will exceed. This one, no worries, but this one will be deprotonated. Now that it's an ion, it's charged and cannot go into the lipid of the lipid bilayer, so it's stuck inside the cell. So as more and more of these cross in, the cell starts to get rich in this impurity, and so it can't shuttle it out. There's no pathway for it to go through. It's too big for a channel. There's no carrier molecule. It can't naturally go through the cell membrane anymore. And so what happens, it's trapped in there. And so even if you start to break it down, you still have a charged metabolite. You have a salt inside the cell, which creates an imbalance. To offset this, you can't shuttle out the particles. So instead, you bring water in. No matter how much water you bring in, you cannot dilute it back to zero because you still have stuff in there. And so the cell will take on water to the point where it finally lyses. It gets so large it bursts. So when it migrates to the cell, this compound will actually start aggregating inside the cells. And if you take too much aspirin, that concentration gets higher and higher and higher to the point where it actually ruptures your cells. So sure enough, aspirin will destroy stomach lining one cell at a time. Okay, and it's a pH-related problem of an organic molecule. So that's why it's so applicable right here. So protonated when pH is less than pKa, but deprotonated when pH is higher than pKa. So the intuitive reasoning, if pH is higher, it feels basic under basic conditions. things get deprotonated. So this is deprotonated, and this is an ion. So the key thing here, this is neutral, so it can incorporate into the cell membrane and traverse it into the core of the cell. This is charged, so it cannot go into the lipid bilayer of the cell membrane, so it's stuck. Okay. If pH happens to equal pKa, so if we had a situation where pH was 5, then it'd be a half and half, or pH of 10, it'd be half and half here. pH equals pKa, its protonated must equal deprotonated. If we think about it, intuitive reasoning, pH equals pKa, it's a little bit of both. It's kind of acidic, kind of basic to it. It feels a little bit of both. So you get half and half. You've compromised between the two. Okay, this is a conceptual perspective. One also considered the Henderson-Hasselbalch mathematical relationship. So the thing just came to the screen. Protonated here, but deprotonated up here. This one I'm just going to ignore. So protonated, protonated, neutral, deprotonated, negative. This can go in, but it can't come out. Okay, the mathematical perspective. The Henderson-Hasselbalch is, again, pH equals pK plus log of AHA, A minus over HA. A minus is the deprotonated form of the base. HA is the protonated form. So math reasoning is this. If the pH is less than the pK, then this is a small number equals a large number plus a negative number. This number can only be negative if the denominator is bigger than the numerator. So if the log term is negative, so pH less than this, the log term is negative, then it must have a larger denominator than numerator. So protonated must be bigger than deprotonated, which means, once again, this confirms pH is less, it's mostly protonated. Equally, for this one, if pH is greater, if this number is larger, then this must be positive. This can only be positive if the numerator is bigger than the denominator. So deprotonated is, in fact, bigger than protonated. So it's exactly what we concluded conceptually, but now we have the math to reason through it. And this is, I think, where the math is really helpful, is now we know specifically, if we plug in equal parts, whatever this is divided over this is, if this is the same as this, number-wise, then it equals 1. Dividing something by itself is 1. Log of 1 is 0, so pH will equal pKa. So that one's pretty straightforward. I hope this equation seems familiar. We will address it. We will go into it a little bit, but it will not be a core part of this class. But it definitely will be a core part of your experience when you take biochem. Okay, so the general information you need to know. So acid dissociation, we call it dissociation because it dissociates, it breaks apart, as opposed to association where things come together. So HA, you place it in the water, so I'm doing the Arrhenius definition. We add it into water, and the water helps facilitate the separation of H plus from A minus. So you get H3O plus and A minus. Equilibrium constants, if you recall, are products over reactants, ignoring pure solvents, so water does not appear in the denominator. pKa is negative log of Ka, much like pH is negative log of H plus. And then just like before, if pK is negative log of Ka, then Ka equals 10 to the minus pKa. Okay. Things you should conceptually know. If an acid gets stronger, as acid strength goes up, that means it dissociates more, so you have more product, so the numerator gets bigger, denominator gets smaller. So Ka goes up, because at negative sign, that means pK decreases, so a lower pK means more acidic. So stronger acids have larger Ks and smaller pKs. We are going to use pKa a lot in this class. That's going to be almost like a boiling point, melting point. We're going to treat it like a physical property that defines relative acidity of compounds. It is absolutely imperative you get that down pat. Base hydrolysis, we call it hydrolysis because hydrolysis. It is being lysed or broken with the help of water. So in this case, the water is breaking into H and OH. And so this is reacting with the help of lysing of water. A minus picks up an H for HA, leaves behind an O minus. So just for consistency of charge, let's see if this works out. Negative and neutral equals neutral and negative, check. Neutral and neutral equals positive, negative, check. Charge is conserved, H's are conserved, all this is good. So the Kb, we call it a Kb because it's a base, products of reactants, ignore the water. And then pKb is negative log of Kb. Kb is 10 to the minus pKb. Again, same logic. And I'm going to add one more step to it. If the acid gets stronger, its conjugate base is said to be weaker. So its base strength decreases. That means it goes less than 4 directions. So numerator gets smaller, denominator gets bigger. Smaller or bigger means Kb decreases. That would mean negative of that would be the pKb increases. So its base strength goes down, Kb goes down, pKb goes up. The consequence are for a conjugate pair like HA and A minus, pKa and pKb operate in opposite fashions. If one goes down, the other goes up. That is because they equal a constant. So pK plus pKb, again, at 25 degrees will equal 14. So overall relationship, we're just going to add this part to this part. Acid goes up, Ka goes up, pK goes down. Conjugate base strength goes down, Kb goes down, pKb goes up. So if you know one of these, you know the other 5 automatically. You just have to remember them. And then again, pK plus pKb for a conjugate pair equals 14 at 25 degrees. Okay, so want to see how this terminology fits? I like to throw multiple choice questions for logic, and I like to throw show your work questions for learning the content. So you're going to see both. So this is the first of many multiple choice questions that we'll be doing on this topic. So conceptually speaking, I have no idea what the question is asking. I'm in trouble. I don't know how to answer it. So this is where a really good vocab will help. Higher ionization constant. So ionization, I know, is breaking apart into ions. And when I'm talking about an acid, because I see a pK here, then greater ionization constant means it's going to dissociate more. It's going to break apart more. So if it breaks apart more, that means you get ionizes more, you get more ions. That means it must be a stronger acid. The more it ionizes, the more H plus you get, the stronger the acid. Greater dissociation is saying the exact same thing. It dissociates more, so therefore, stronger acid. If it's a better electron acceptor, it means it's a better Lewis acid. So I'm just going to drop the word Lewis and say it's a better acid. Better acid would mean stronger acid. And then increased pKa, that's just defined as a weaker acid. We just went through that in the list. So if you go through these answer choices, A, B, and C are all the same answer. They're all stronger acid. So I can't pick them all, so it must be wrong. So D must be my best answer. So the point I'm making is there will be multiple choice questions in your life. It'll be on your exams. It'll be on standardized exams. It'll be on licensing exams. It'll be everywhere the rest of your life. Learning multiple choice logic helps. And then also realizing that the more you know definition-wise, the more you can think your way through a question. Okay, so 13 is in the books. I think actually 15 is in the books, my mistake. And we will go on to the next. I will see you at the next Toddcast, which will be 16. So have a wonderful time studying and see you soon.